In my today's lecture, I want to discuss the components of the wind machine and mills, their constructional features of the components. The wind power system comprises one or more wind turbine units operating electrically in parallel. Each turbine is made of the following basic components. Number one, this is the blade. Number one, this is the blade. Number two, this is the rotor. This is the rotor. Number three, this is the pitch. Number four, this is the brake. Number five, this is the low speed shaft. Low speed shaft. 6 is the gearbox. This is the gearbox. 7 is the generator. This is the generator. 8 is the controller. This is the controller. 9 is the anemometer. Anemometer. Wind vane. This is the wind vane. This is the nacelle. Nacelle is the cover. 11. This is the nacelle. 12 is the high speed shaft. This is the high speed shaft. Jaw drive. These are the jaws are there. 13. This is the jaw. And the jaw motor. 14. This is the jaw motor. And 15 is the last. This is the tower. So now come to the elaborate description of the components. First is blades. Most turbines have either 2 or 3 blades. Wind blowing over the blades causes the blades to lift and rotate. Blades come in various sizes and have tended to grow over the years. In the early 1980s, a typical blade was likely to be 33 feet, that is 10 meters long, and such a wind turbine could generate about 45 megawatt hour per year. By 1990, the typical blade measured 89 feet, that is 27 meters, and could produce 550 kilowatt hour per year. In the early 21st century, the blades as long as 233 feet, that means 71 meters, it can generate 5,600 megawatt hours per year. Modern wind turbines have the 2 or 3 blades which are carefully constructed airfoils and utilize the aerodynamic principles to capture as much power as possible. The airfoil design uses a longer upper side surface, whereas the bottom surface remains somewhat uniform. Blade designs operate on either the principle of drag or lift. Now come to the second component, that is called the rotor. The rotor is the hub around which the blades are connected. This is the rotor. Often, however, the rotor is used to refer to the hub and the blades as a single unit. This figure is the simplest figure of the wind turbine design. This is the hub. The rotor is the key component because it translates the wind's kinetic energy into the torque or the turning power. Rotor size is determined by the power output that the machine is designed to develop. The larger the diameter of the rotor, the more energy it can capture. A 600 kilowatt wind turbine will have a rotor diameter of 40 to 50 meter, while a 5 megawatt machine needs a rotor diameter of around 120 meter, rising to 140 meter for 6 megawatt. Rotor sizes for offshore machines tend to be slightly larger than those of the onshore machines for a similar output. The offshore wind power, sometimes referred to as the offshore wind energy, is when the wind over the open water, usually in the ocean, is used to generate the power. Wind farms are constructed in bodies of water where the higher wind speeds are available. The advantage of the offshore windmills that the windmills can be built that are larger and taller than their onshore counterparts, allowing for more energy collection. They tend to be far out at sea, meaning they are much less intrusive to the neighboring countries, allowing for larger farms to be created per square mile. Typically, out at sea, there is a much higher wind speed or force, allowing for more energy to be generated at a time. Wind farms have a relatively negative impact on the environment. They are not built in shipping lanes, fishing areas, or in a delicate environment. There are no physical restrictions such as hills or buildings that could block the wind flow. The disadvantages of the offshore wind, that is the biggest disadvantage of an offshore wind farm is the cost. Onshore wind farms can be expensive to build and maintain, and because of their hard to reach locations, they are susceptible to damage from very high speed winds during the storms or the hurricanes, which is expensive to repair. The effect of the offshore wind farms on marine life and birds are not yet fully understood. The offshore wind farms that are built closer to the coastlines, generally within the 26 miles, can be unpopular with the residents as it can affect property values and the tourism. On the other hand, the onshore wind power refers to the turbines that are located on the land and use wind to generate the electricity. They are generally located in areas where there is low conservation or the habitat values. The advantage of this type of onshore wind mills that the cost of onshore wind farms is relatively cheap, allowing for mass farms of the wind turbines. The shorter distance between the windmill and the consumer allows for less voltage drop-off on the cabling. Wind turbines are very quick to install, unlike a nuclear power station which can take over 20 years. A windmill can be built in a matter of months. There is some disadvantage of the onshore windmills. That is one of the biggest issues of the onshore wind farms is that the many deem them to be an eyesore on the landscape. They don't produce energy all year round due to the often poor wind speed or physical blockages such as buildings or hills. The noise that wind turbines create can be compared to as the same as a lawn mower, often causing noise pollution for nearby the communities. The the rotational speed is also a factor in the rotor design. It is normally necessary to keep the speed at which the tip of the rotor blades move through the air to below the 70 meter per second in order to minimize the aerodynamic noise, which can become an environmental problem. This means that as the rotor diameter increases, the rotational speed must decrease. Current 2 to 3 megawatt designs normally rotate at between 5 to 20 rpm. The third component is the pitch. This is the pitch. Blades are turned or pitched out of the wind to control the rotor speed and keep the rotor from turning in winds that are too high or too low to produce the electricity. This involves a rotor with blades that can be twisted at different wind speed, as shown in the figure. This can be twisted to increase or decrease their aerodynamic effectiveness. Pitch control has an additional advantage of allowing some power output control, which can lead to better efficiency of operation. This system has become the most popular method of the speed control. Next, the component is the brake. This is the brake, a disc brake which can be applied mechanically, electrically or hydraulically to stop the rotor in energies. There is two types of brakes are there. One is aerodynamic braking system and another is the mechanical braking system. First is the aerodynamic braking system. The primary braking system for most modern wind turbines is the aerodynamic braking system, which essentially consists in turning the rotor blades about 90 degrees along their longitudinal axis, or in turning the rotor blades tip the 90 degrees in the case of stall control turbine. These systems are usually spring operated in order to work even in case of electrical power failure, and they are automatically activated if the hydraulic system in the turbine loses the pressure. The hydraulic system in the turbine is used to turn the blades or blade tips back in place once the dangerous situation is over. It is experienced has proved that the aerodynamic braking systems are extremely safe. They will stop the turbine in a matter of a couple of rotations at the most. In addition, they offer a very gentle way of braking the turbine without any major stress, tear, and wear on the tower and the machinery. The normal way of stopping a modern turbine is therefore to use the aerodynamic braking system. The second type of braking system is the mechanical braking system. The mechanical brake is used as a backup system for the aerodynamic braking system and as a parking brake once the turbine is stopped in the case of a stall control turbine. Pitch control turbines are rarely need to activate the mechanical brake except for maintenance work, as the rotor cannot move very much once the rotor blades are pitched 90 degrees. Now the fifth component is the low speed shaft. This is the low speed shaft. I am just pointing out, this is the low speed shaft. The rotor turns the low speed shaft at about 30 to 60 rotations per minute. It is connected to the gearbox, to the rotor. The gearbox is the sixth component. This is the gearbox. The gears connect the low speed shaft to the high speed shaft and increase the rotational speed from about 30 to 60 rotations per minute to about 1000 to 1800 rpm, the rotational speed required by most generators to produce the electricity. This is the low speed shaft and this is the high speed shaft. So the gear is connected in between the low speed shaft and the high speed shaft. The gearbox is a costly and very heavy part of the wind turbine, and engineers are exploring the direct drive generators that operate at lower rotational speeds and don't need the gearboxes. This gearbox has to be extremely rugged because it must be able to withstand more than simply the rotational force from the wind turbine rotor. The seventh component is the generator. The generator is what converts the turning motion of a wind turbine blades into the electricity. This is the generator, the seventh component. The electric generator in a wind machine is attached to the main support frame and coupled to the high-speed end of the transmission shaft. Alternating current generators often run at 1800 rpm in USA or 1500 rpm in much of the world to maintain the system frequencies of 60 Hz and 50 Hz respectively. Inside this component, the coils of wire are rotated in a magnetic field to produce the electricity. Different generator designs produce either the alternating current or the direct current, and they are available in a large range of output power ratings. The generator ratings or size is dependent on the length of the wind turbine's blades because more energy is captured by the longer blades. The conversion of the rotational mechanical power generated by the rotor blades into the useful electrical power for use in domestic power and lighting applications or to charge batteries can be accomplished by any one of the following major types of rotational electrical machines commonly used in a wind power generating systems. There are three types of generators are used in the wind turbines, that is the direct current machine, also known as the dynamo, the alternating current, the synchronous machine, this is called the AC generator, and the third type is the alternating current induction machine, which is also known as the alternator. All these electrical machines are electromechanical devices that works on the Faraday's law of the electromagnetic induction. That is, they operate through the interaction of a magnetic flux and an electric current or flow of charge. As this process is reversible, the same machine can be used as a conventional electrical motor for converting the electrical power into the mechanical power, or as a generator converting the mechanical power back into the electrical power. The electrical machine most commonly used for the wind turbines applications are those acting as the generators, with the synchronous generators and the induction generators being commonly used in larger wind turbine generator system. Usually, the smaller or the homemade wind turbines tend to use a low-speed DC generator or the dynamo, as they are small, cheap, and a lot easier to connect up. The low voltage DC output from a generator or older style dynamo can be used to charge the batteries, while the higher AC sinusoidal output from an alternator can be connected directly to the local grid. The simple generator using the magnetic induction are shown in the figure. All the electrical turbine generators work because of the effects of moving a magnetic field passed on the electrical coil. When the electrons flow through an electrical coil, a magnetic field is created. This is the magnetic field, the rotating magnetic field. This is the rotating shaft, the magnet is rotating, and this is the line of flux, and the magnetic field is created and it is rotates along the magnet. When the electrons flow through the electrical coil, a magnetic field is created around it. When a magnetic field moves past a coil of wire, a voltage is this is the coil. A voltage is induced in the coil as defined as Faraday's law of the magnetic induction, causing the electrons to flow. Then we can see that by moving a magnet past a single loop of wire, a voltage known as the EMF, that is called the electromotive force, is induced within the wire loop due to the magnetic field of the magnet. As a voltage is induced across the wire loop, an electrical current in the form of an electron flow starts to flow around the loop, generating electricity. But what if instead of a single individual loop of wire as shown, we had many loops wound together on the same former to form a coil of wire? Much more voltage and therefore current could be generated for the same amount of magnetic flux. This is because the magnetic flux cuts across more wire, producing a greater EMF, and this is the basic principle of the Faraday's law of electromagnetic induction, and an AC generator uses this principle to convert a mechanical energy such as the rotation from a wind turbine or the hydro turbine into the electrical energy, producing a sinusoidal waveform. This is the sinusoidal waveform. So we can see that there are three main requirements for the electrical generation, and these are a coil of set of conductors. These are the coil of set of conductors, a magnetic field system, and the relative motion between the conductors and the fields. Then the faster the coil of wire rotates, the greater the rate of the change by which the magnetic flux is cut by the coil, and the greater is the induced EMF within the coil. Similarly, if the magnetic field is made stronger, the induced EMF will increase for the same rotational speed. Thus, the induced EMF is proportional to the phi cross n, where phi is the magnetic flux and n is the speed of rotation. Also, the polarity of the generated voltage depends on the direction of the magnetic lines of flux and the direction of movement of the conductor. There are two basic types of electrical generator and alternator for the matter: the permanent magnet generator and the wound field generator, with both types consisting of two main parts. One is stator and another is rotor. The stator is the stationary part of the machine and can have either a set of electrical windings producing an electromagnet or a set of permanent magnets within its design. The rotor is the part of the machine that rotates. Again, the rotor can have output coils that rotate or permanent magnets. Generally, the generators and alternators used for the wind turbine generators are defined by how they generate their magnetism, either electromagnets or the permanent magnets. There are no real advantage and disadvantage of both of the types. Most residential wind turbine generators on the market use the permanent magnets within their turbine generator design, and which creates the required magnetic field with the rotation of the machine, although some do use the electromagnetic coils. These high strength magnets are usually made from rare earth materials such as the neodymium iron or the samarium cobalt, eliminating the need for the field windings to provide a constant magnetic field, leading to a simpler, more rugged construction. Wound field windings have the advantage of matching their magnetism with the varying wind speed, but require an external energy source to generate the required magnetic field. The wind turbine generator output curve, very much important properties of the generator. The generator will not produce output power until its rotational speed is above its cut-in wind speed. This is the cut-in wind speed, where the force of the wind on the rotor blades is enough to overcome the friction and the rotor blades accelerate enough for the generator to begin the producing usable power. Above this cut-in speed, the generator should generate the power proportional to the wind speed cubed until it reaches its maximum rated power output as shown in figure. This is the maximum rated power output. Above this rated speed, the wind loads on the rotor blades will be approaching the maximum strength of the electrical machine, and the generator will be producing its maximum or rated power output as the rated wind speed window will have been reached. This is the maximum rated power wind speed window, rectangular window. If the wind speed continues to increase, the wind turbine generator would stop at its cutoff point. This is the cutoff point. The cutout point to prevent the mechanical and electrical damage resulting in zero electrical generation. The application of a brake to stop the generator for damaging itself can be either a mechanical governor or by the electrical speed sensor. Now another component, the eighth component, is the controller. This is the controller. The controller starts up the machine at the wind speeds of about 8 to 16 miles per hour and shuts off the machine at about 55 miles per hour. Turbines do not operate at wind speeds above about 25 miles per hour because they might be damaged by the high winds. The ninth component is the anemometer. It measures the wind speed and transmits the wind speed data to the controller. 10th component is the wind vane. This is the wind vane. This is the anemometer and this is the wind vane. It measures the wind direction and communicates with the jaw drive to orient the turbine properly with respect to the wind. The 11th component is the nacelle. The nacelle is the enclosure that houses the turbine's drivetrain, including the gearbox, the jaw mechanism, and the electrical generator. The gearbox connects a low-speed shaft to a high-speed shaft. This mechanism can increase the speed of the shafts by a factor of as much as 50 to 1, meaning that the high-speed shaft turns 50 times faster than the low-speed shaft. The high-speed shaft. This is the high-speed shaft. 5 is the low-speed shaft and 12 is the high-speed shaft. It drives the 13 is the jaw drive. This is the jaw drive. The jaw mechanism automatically senses the direction of the wind and rotates the rotor to keep it facing into the direction of the wind. Downwind turbines don't require the jaw mechanism or the jaw drive. the winds blows the rotor downwind. 14th is the jaw motor, powers the jaw drive. The last component is the tower. The towers are made from the tubular steel, concrete, or the steel lattice. This is the tower. Because the wind speed increases with the height, taller towers enable turbines to capture more energy and generate more electricity. The wind tower supports the rotor and the nacelle containing the mechanical gear, electrical generator, jaw mechanism, and the stall control. The height of the tower in the past has been in the 20 to 50 meter range. For the medium and large size turbines, the tower height is approximately equal to the rotor diameter. The small turbines are generally mounted on the tower a few rotor diameters height. Otherwise, they should suffer fatigue due to the poor wind speed found near the ground surface. Both the steel and the concrete towers are available and are being used. The construction can be tubular or the lattice. Towers must be at least 25 to 30 meter high to avoid the turbulence caused by the trees and the buildings. Utility scale towers are typically twice as high to take the advantage of the swifter winds at those heights. The main issue in the tower design is the structural dynamics. The tower vibration and the resulting fatigue cycles under wind speed fluctuations are avoided by the design. This requires careful avoidance of all the resonance frequencies of the tower, the rotor, and the nacelle from the wind fluctuation frequencies. Sufficient margin must be maintained between the two sets of frequencies in all the vibrating modes. The resonance frequencies of the structure are determined by complete modal analysis, leading to the eigenvectors and eigenvalues of complex matrix equations representing the motion of the structural elements. The wind fluctuation frequencies are found from the measurements at the site under consideration. Experience on a similar nearby site can bridge the gap in the required information. Big cranes are generally required to install these wind towers, gradually increasing tower height. However, is bringing a new dimension in the installation process. Large rotors add to the transportation problem as well. T-level towers to the nacelle and rotors moving upwards along with the tower are among some of the newer developments in wind tower installation. The offshore installation comes with its own challenge and it must be met. These are the references from which I make the tutorials. Please go through these references. Thank you.